My name's Brendan Donnell, and I'm the Secretary for Engineers for Social Responsibility. Tonight, we're very happy and full of anticipation to hear from Ralf Kessel from Concrete New Zealand, who will speak to us on the subject of the path to net zero carbon concrete by 2050. I'll just make a few brief comments by way of introduction for Ralf. First one is just to talk about Concrete New Zealand. Now, I'm a structural engineer, and 20 years ago, Concrete New Zealand didn't exist. There was a range of different industry groups, such as Cement and Concrete Association of New Zealand, Concrete New Zealand, Ready Mix Concrete Association, and others. And in 2017, they all joined forces to create a larger, powerful organisation that can represent the concrete industry across many facets, and that's Concrete New Zealand. And they've been working hard over the last few years to develop a roadmap to net zero carbon for Aotearoa New Zealand concrete industry. It's an initiative that has led them to link to other international initiatives by other concrete industries around the world, and also has firmly in mind the New Zealand legislation of the Climate Change Response Amendment Act, or Zero Carbon Act, where the country has set the target to reduce our emissions to net zero by 2050. So it's great to have Ralf join us to speak to that today. Ralf's the head of architecture at Concrete New Zealand. There are a number of architects as well as engineers involved with the ESR, and Ralf comes to us with experience from New Zealand, Germany, and the UK. He's been with the Cement and Concrete Association, now Concrete New Zealand, since 2009, which is represents a lot of experience there. And he's been involved in a lot of quite high-profile guidance documents that have been developed and even cited in the New Zealand Building Code. So excellent experience. It's great to have you join us, Ralf. Just to plot out the rest of the talk, we'll open the presentation for Ralf, and he'll speak through his prepared material. At the end, I'm suggesting we have a few questions. So if you have a question for Ralf, we can open the floor for questions and answers at the end. And then we'll finish the recording. And then after that, if people have comments or discussion points, we'd like to, perhaps talk about something or tell a story. If we save that for after the recording has completed, that would be great. So without taking up any more of the oxygen in the room, I'll hand over to Ralf. Welcome, Ralf.
Yeah, thanks very much. And I feel very honored to speak to your members today. It's really a great honor. And as I said earlier, ESR has really huge relevance, and it's just growing. And hopefully you get many more also younger people from the construction workforce, not just engineers, architects, construction managers, and all the likes. That would really help, because only together we can fulfill our duties in regards to social responsibility. But I'd say most 90% of the people have recognized that we have to do something. So I will share my screen, and I always have to do it via a beautiful landscape from New Zealand. But here we go with the it should start. Yeah, now this is coming up, and I believe everybody can see that. And Brendan, thanks very much for the introduction. So everything has been said here, but I understand I have a little bit of time. So I would like to point out a couple of other things before we go towards our sustainability and roadmap. So you mentioned a few things here in regards to our industry already. And yeah, so I just want to add a little bit to that. So yeah, the Cement and Concrete Association was the association I joined in 2009, and we had several concrete associations existing parallel, like the New Zealand Precast Concrete Association, the Concrete Masonry Association, the Learned Society, etc., and to speak with a unified voice and together all our strength into one unit. We just thought it's better to have this overarching association called Concrete New Zealand. So our industry, in a nutshell, we produce about maybe 4.5 million cubic meter of concrete per year, and this activity creates more than 10,000 jobs. And the revenue sits a little bit over $1.1 billion towards our New Zealand GDP. However, this activity also comes with carbon emissions, and our industry, as every other industry, will have to reduce emissions to address climate change and also to comply with New Zealand regulation, the zero carbon bill, for example. So, but I also want to like to talk a little bit about concrete in the past and how concrete can help to get on to the task. So social responsibility to me means that groups and also individuals are accountable for fulfilling their civic duties, and all actions must benefit the whole of society. There must be a balance between economic growth, well-being, and protecting the environment. And as concrete industry, we have this responsibility as a group, but also as individuals. Whilst concrete carbon emissions are relatively modest, the issue is that it is the most consumed resource after water. That's why we have to deal with carbon emissions, which amount to, well, estimated 6 to 8% of all global emissions, human-made, carbon emissions. So, yeah. So, and I believe concrete has a role to play in a social responsible society. With concrete, we can contribute to the well-being of people. Severe weather events have highlighted the need to focus on the twin imperatives of climate change, mitigation and adaptation. So not just mitigation, we have to adapt, unfortunately. The impacts from climate change are severe, and adaptation to weather events is necessary when reducing emissions at the same time. For example, adaptation to floods. There are some great examples what other jurisdictions have done. For example, in the USA, this is an example from Seattle, Elliott Bay, where they have replaced an existing timber steel retaining wall and seawall by this concrete wall. It's a great engineering feat, very sophisticated, which includes a marine mattress at the bottom, protecting sea life living in shallow pebbly ground pockets like crevices and vegetate and other smaller animals hiding places also for young salmon, as I heard. This is the same project, so there is light penetrating through this concrete part because they've included glass bricks, so light can get to the habitat area beneath, which again is very important to the smaller parts of the marine life. Textured wall faces allow for growth of shells and other living organisms. And again, the habitat bench creates a habitat for and hiding space for marine life living in shallow waters. So that's one example how we can not only protect our communities and help from erosion of the land, but also do something for the entire environment, for the marine life as well. Well-being means also the right environment to recharge the batteries, which would be difficult in the noisy surroundings. So concrete helps to adapt to changes in the urban environment. For example, sound protection at highways, airports, etc. Here, this is an example. Many of you will be familiar with that. It's at Auckland Ellerslie. And Just for your benefit, how concrete performs, a 150 millimeter concrete board provides already 55 decibel of sound attenuation. An acceptable noise level in homes are around the 30 decibel, 35 maximum, and maybe 25 in bedrooms. For comparison, a jackhammer from a 3-meter distance comes with about 90 decibel. So minus 55 decibel sound attenuation by a wall makes 35 decibel, and obviously the further the noise source away, the better it is. 55 decibel is also the minimum required for partition walls in medium density housing for compliance with our clause, building code clause G6. Again, a 150 millimeter wall provides that concrete or in situ or precast, or a 200 millimeter or 190 millimeter fully filled concrete masonry wall. So the sound attenuation, that's a big feature from concrete structures. However, there are two differences. There's the airborne sound, which is generated by traveling through the air, for example, by speaking. And then there is impact sound, which is usually generated by an impact onto a medium like a drum, or like stepping onto a slab. And for airborne sound, we say mass is, the more mass, the better. But for impact sound, we have to, in addition, separate the structural or the stepped on surface from the structure beneath, which can be done in New Zealand, for example, by a carpet and an underlay. In Germany, it's mandatory for medium density housing, such as this here, to have a floating screed. So there's a 40-50 millimeter floating screed sitting on, let's say, 15 to 20 millimeter sound insulation material, which can be made of recycled tires or anything else which is sound absorbing. And the sound protection is wrapped around the edges of the floating screed to avoid sound flanking via the walls. This is mandatory and standard for buildings in Germany. No wonder building in Germany is very expensive, much more expensive than in our neighboring countries like Holland or France or Italy or the eastern countries. However, concrete is vital to addressing the housing shortage. We will see more medium density developments. Concrete buildings are strong, can house many apartments, all of which are separated by inherent fire protection walls with noise attenuating properties. For our well-being, it's important that we can live in homes that give us peace of mind, that protect us from the impacts of earthquakes, from weather events, but also from maybe burglary. So it's important we feel safe. And again, a concrete home can deliver that. Also, in regards to energy and saving resources, energy resources, if designed and applied correctly, like an exposed concrete floor or walls, they give you the benefit of heat storage, of thermal mass. So in summer, it will take up some of the heat to reduce overheating, and once temperatures drop, it will release the heat back into the space. And in general, it balances the climate as well between the swings. So it's never as hot and never as cold as in buildings which don't have thermal mass. This is in-service history of concrete structures lasting long, having adapted through millennia, a testimony of durability. Rome's Pantheon, about 2,000 years old. Concrete structure, very interesting concrete structure. Obviously, back then they did not have cement, they did not have Portland cement. They took their cement or their glue or their porcelain just out of nature. They took it from volcanic limestone, from volcanic ashes. And they also have included empty clay jugs into the top areas of the dome, just to create some air pockets, to create voids, to reduce the weight. It's a very, very interesting building. Possibly many have seen it in Rome. There's this always open oculus providing light and some form of ventilation. And if it rains, it really just goes in kind of into the middle. So it's a very, very interesting building, and stunning 2,000-year-old concrete surface, fair face concrete surface. Concrete is vital to a change in New Zealand. We have our communities, also our elderly, who must be included into the society. They want to meet with younger people, and we need those shared spaces, maybe gardens where the young and the older ones and the middle ones grow their veggies and plants together. And the surrounding and everything should be made durable, that the spaces can be used for a long time without needing repair or replacement. In 2019, the IPCC, Intergovernmental Panel for Climate Change, has recognized concrete as a carbon sink. There have been studies since many time. One person did a bit of research and looked over the potential carbon storage from since the 1930s to today, and he had some amazing results there. So how much carbon is absorbed by concrete can be calculated by an appendix to EN 15804. So that only accounts for the externally exposed concrete, where there is carbon in the air, and then concrete can take up parts of the carbon. EN 15804 is the standard or the norm to creating EPDs, environmental product declarations, and the British Research Establishment has developed the formulas and the standard for how much carbon is actually absorbed by per square meter of exposed concrete. It depends on many things. It depends on the concrete, on the quantity of cement, of supplements, and a couple of other things. So there are various formulas which can be used by engineers. I don't say it's super easy, but for engineers, you are all very clever and logically thinking people. I think for you, it should be relatively straightforward to use those formulas. So once again, I believe concrete is vital to change in New Zealand, and we can definitely contribute to an environmental friendly and a prosperous New Zealand for the future with our properties of the material concrete. So our structures are strong, durable, fire resistant. They provide sound attenuation. We have thermal mass. Concrete homes give you a good, safe feeling. Exposed concrete is a natural carbon sink, and we are able to create structures helping to adapt to the impacts from climate change. So again, one more little chapter before I go to our roadmap. So let's have a look at some applications of concrete, and here the benefits of concrete roads. For example, concrete roads typically have a 40-year design life, and during that time require minimal maintenance. In contrast, asphalt surfaced flexible roads last about 25 years and require regular repairs and maintenance, particularly if heavy vehicles cross the street. And it's not just the costs and the resources for the repair or replacement, but it's also the disruption of the traffic, leading to maybe traffic jams, noise, dust, dirt, etc. So I think there's always a benefit if we use a durable material. The little grooves you see here, they are brought into place to prevent skidding, the cars from skidding. I'm aware of a study of the Massachusetts Institute of Technology. They looked into the fuel efficiency and also durability, comparing concrete with asphalt road. So in the essence, what they say, asphalt roads are softer, and cars, and again, especially trucks, will partly sink into the softer surface, which increases the fuel consumption. So if the surface is rigid, cars normally roll more smoothly and more above the surface. So that will definitely save a little bit on the fuel side of things as well. Concrete roads up front are a little bit more expensive, but after about 10 to 12 years, it will turn around because concrete roads need less maintenance. Another common applications are buildings. This is a very prominent development by Aotearoa. This is the Beta Ventura Drive in Auckland, the first passive house certified medium density housing development in New Zealand. And that's made of concrete floors and slabs, and the walls are made of precast insulated sandwich panels delivered by Concrete Tech in Auckland. And again, it has been passive house certified by Jason Quinn is his name, sustainable engineer, and he was also the first passive house certifier in New Zealand. So that's a very interesting building and project. In general, for buildings and homes, again, the homes provide the safety, security, fire safety, and the performance of concrete walls and floors and structures in regards to the provisions of fire safety minutes. That's all described in 3101 and partly in 4230 for the masonry structure. For example, 100 millimeter thick concrete wall gives you already 2 hours of fire protection. 165 millimeter adds up to 3 hours. So, and a little bit more, you at 4 hours. So it's very good in regards to fire performance and noise. We talked about that. G6 sound attenuation through to mass. Thermal mass. Also, if you use exposed concrete floors, it doesn't contain any volatile organic compounds, and we can make sure that the building will last. And again, repairs. That's not just the money. It's really stress to the people. It's financial stress. It's noise. It's dirt. So it's just good to avoid repairs, and of course we save resources and labor. Other important applications for our society are landscaping and townscaping environments. This is a beautiful example here from Lithuania, where kids play in the water features and grown-ups have a chat. This is also bus traffic proof. Some of you may be from Christchurch here, and I remember Christchurch about 10 years ago or 12 years ago. They had some issues with natural stone pavement around the Cathedral Square. The paving was not up to take on bus traffic loads and loosened all over the place. And the consequence was that the natural stone pavement has been replaced by concrete pavement, which is able to take up the heavier loads from bus traffic. Also landscaping here on the left bottom, left top side, that's beautiful structure made of mushroom-like concrete columns of the various heights. I've been there myself, so this is in New York, in the Hudson River. It's really stunning. It provides for recreation. There's a stage, there are workout areas, there's a jogging path, it goes up and down, there are lots of places to relax. It's just a really stunning feature, kind of regaining or gaining land without losing actually area in the water too much. This is also an example which I like very much, very sustainable. They use demolition waste, concrete demolition waste for their retaining walls, for their stairs, for the pathways. And I've seen several of these also in New York, actually around the High Line. You've heard about the High Line, which is a seized subway, tram, public transport train, and now it's a public park. And that's a great feature, also having some of these reused concrete elements featuring on the platforms there. Then, of course, pervious concrete, which allows rainwater, stormwater, rainwater going directly through the paved surface into the soil, which is relief to our sewerage and drainage systems. So that has been used frequently for pathways, for walkways, and also in residential areas around schools. It's particularly great for car parking, where the cars are parked. For actual roads, it's not recommended because it's not really strong enough, but for a cycle and for pedestrian and for just for standing cars, it's very suitable. The other option always is permeable concrete paving systems. Protection, adaptation to sea walls. So concrete can definitely help to adapt to the impacts of climate change. And I think we all remember the sad, terrible events from last year, the flooding in the area of Gisborne, and in that area that was really terrible. But concrete can help to adapt to rising sea levels by creating walls, concrete walls that can be covered then again with some soil, which of course will washed away over the time. But you will find also that smaller marine life will find their pockets here in the newly built sea walls. This is an example from St. Kilda in Dunedin, near the swimming pool, which is a stunning feature. The swimming pool surrounded by concrete as well, and I like it when the water's sometimes coming over the wall actually into the pool on very stormy days. Concrete helps to connect our societies. Concrete helps to deliver goods, food to people. Concrete enables businesses. Here two great examples of really high-tech concrete engineering. Well-executed engineering features the Storebælt Bridge in Denmark, connecting parts of the country over kilometers, or the Sutong River Bridge in China here, which is even longer, a tall concrete bridge, also carried by steel cables. So, so really stunning examples we have in infrastructure. Other examples are museums, theaters, schools, swimming pools, or the women's hospital here in Christchurch, which was able to withstand the earthquakes in 2012 more or less without damage, whilst the building next door had to be completely demolished. So the women's hospital is actually a concrete structure sitting on base isolators, and as engineers you know that on base isolators the structure should be rigid so that the building moves in its entirety. If it would be a ductile building, you would experience swings amplifying to the top of the structure and leading potentially to collapsing then. So this has performed well on base isolators. There are other great examples. Base isolated building, the Te Papa in Wellington, also the library in Wellington, even retrofitted a couple of buildings at the university in Wellington as well. So there are systems in place. The other one would be the we all know Nigel Priestley's press system. So there are definitely systems in place, and again, this is not really so much a matter of material, but more of design, of engineer design to create these damage avoiding buildings. Concrete is also important to get to our 100% renewable target. We are very, very fortunate in New Zealand that we have already about 80% renewable energy, thanks to hydropower, thanks to wind power, and also thanks to geothermal power. So this is an example from Waikato. There are several smaller dams creating these the hydro dams and hydropower. And then we have an example here from Wellington at Makara, the wind turbines, and obviously it's not about the gravity loads, even they are heavy. It's more about the wind loads pulling on the foundation. So we have huge concrete foundations sitting beneath the wind turbines here. So they're all really important examples how concrete can help us. And then, of course, one of the possibly the most common application of concrete in New Zealand are slabs on ground and slabs for driveways, etc. You are familiar with the, well, they're no longer new, but after the Christchurch earthquakes, we changed a little bit the reinforcements, 2D12s here into a 1D12 here and a 500 mesh in the middle of the slab. And then, of course, retaining walls, ensuring land does not collapse around buildings, around roads and tunnels, and around the infrastructure. So there's definitely a reason of why concrete is the most used material on Earth. And yeah, you just saw a couple of examples here: the roads, the buildings, landscaping, adaptation, seawalls, infrastructure, energy generation, foundations, and so forth. So there are good reasons to use concrete. However, the benefits of concrete are well documented, but as any other material, we must cut our carbon emissions. About 80% of all the emissions associated with concrete are coming from cement production. And here, if we look at cement production, 40% of the emissions from cement production are coming from the use of fossil fuel, which is mostly coal. But the larger part, 60%, are developed in a chemical process when we separate lime from the limestone within the kiln. That's a chemical process called calcination, and we have to work on reducing our emissions. And as I said, in itself, concrete is a low carbon material. 1 ton of, say, 25 MPa concrete comes with about 100 kilogram of carbon per ton. So per cubic meter, that's 230, 240, 230, I think it's first average at the moment, per cubic meter per ton, given the density of 2.4 ton per cubic meter. So that's around 100 kg per ton. 100 kg, in comparison, aluminium comes with 20,000 kilogram per ton. But of course, aluminium is not used in the quantities as we use concrete. Aluminium is really just there for maybe windows, a couple of other smaller things. So because concrete is the most produced and most used material in the world, we find a huge sum of carbon as a result, estimated to be between 6 and 8% of man-made carbon emissions, 14 billion cubic meter or 35 billion tons production globally per year. That's about 3.5 billion ton of carbon, and that's huge. So in 2021, the Global Cement and Concrete Association launched the Global Industries Decarbonisation Roadmap to 2050. And Concrete New Zealand and our members are all on board, are all in line with their goal. And also, by the way, just to mention it here, at the next Climate Summit 28 in Dubai, the Global Cement and Concrete Association is hosting a pavilion on cement and concrete industry decarbonisation, and will report on the progress. Another 4 years away, and the roadmap, the initiative has been recognized by the UN, by Antonio Guterres. And the roadmap forms part of actually a global initiative. Of course, every country is different. Every country has different resources, but in the essence, we follow suit. But we have developed our own roadmap, which I will talk about as well in a minute. So the quick summary where concrete emissions come from. So here we have the transport of raw materials, aggregates, etc. The emissions from aggregate generations are pretty low, but the biggie is here, direct emissions from chemical reaction and from burning fuel, which I just explained, the calcination process and the coal to heat the kilns. That's the 80%. Then we have another, call it whatever, 4% from 3% from transport, and another 8%, maybe 10% at the plant, at the batching process and everything associated with that. And then again, depending on the distance, obviously the transport from the batch to the building site. And well, there is a little movie here. I'm not sure if I should show it because it's a little bit, well, yeah, maybe we just put it on if it works. It's just 2 minutes.
Block of civilization. As Aotearoa, New Zealand moves towards a more sustainable future, the concrete industry is making changes to be net zero carbon by 2050. Concrete New Zealand's membership makes a significant contribution to our construction sector. Together, we're committed to playing an important role in mitigating climate change by reducing concrete's carbon emissions. In fact, we've already started our decarbonisation journey. Between 2005 and 2020, the industry reduced CO2 emissions by 11%, even though ready-mixed concrete use increased significantly during that time. We've also developed a roadmap that will ensure our place in 2050 is sustainable, circular and net zero carbon. It will require a collective effort from ourselves, our construction and research partners and the government to achieve this goal. Here's how. Increasing the use of alternative fuels to replace coal in making cement clinker. Partial replacement of cement with low carbon, natural or recycled materials. Efficiencies in concrete production. Design and construction optimisation. Recognising carbon uptake, which sees exposed concrete absorb CO2. Further decarbonising New Zealand's electricity grid. And capturing remaining CO2. Concrete is essential to New Zealand's future resilience. It offers fire resistance and adaptability. Concrete is also strong, durable and thermally efficient in the face of extreme weather events that will become more common with climate change. There's a long road ahead, but we have a plan and the ambition to achieve a net zero carbon concrete industry for Aotearoa, New Zealand by 2050.
So thanks for listening to that. So what does this actually mean? Oops. So as we heard, we have already reduced our emissions by 11% since 2005 values, and this against an increase of concrete production. So we are now in the middle of 2020, which is the decade. The 2020s are the decade, is the decade to deliver. So what have we done so far? For example, Golden Bay Cement have replaced parts of the coal used to heat the kilns by waste timber. They still cannot replace all of the coal because some of coal heat is so specific, very strong, which we still need. But a beginning is done, and you can see that alone last year, 38,000 tons of waste timber has been incinerated, has been used replacing coal as a fuel for the cement kilns. And then the first ever undertaken EPD, the first ever undertaken environmental product declaration in New Zealand was published 10 years ago, and it was commissioned by Allied Concrete. So the concrete industry had the first EPD done in July 2014. So this was the first, so concrete was the first material with EPDs in New Zealand. This is and was helping towards accurately monitoring our progress and to defining clear reduction targets. So in the meantime, many of our concrete manufacturers have produced their EPDs. Firth, Bridgman, Stevenson, Higgins, you name them, they all have their EPDs. Here is the example from Firth EPD, and I put up the 25 MPa mix. As we can see, the average, South Island average is 230 kilogram per cubic meter. So these are all cubic meter units, so which is a little bit less than 100 kilogram per ton. Even less in Blenheim, there's only 215 kilogram per cubic meter. So it's great to have the data, and yeah, obviously we have to get lower beneath these numbers. Firth, for example, use Golden Bay Cement, Allied use Holcim Cement, and Holcim have also opened now their own concrete manufacturer in November in New Zealand. So the next stage would definitely be cement supplements of these already low figures. So, and what does it mean? How does it look like? Cement, we call cement supplements supplementary cementitious materials, in short SCMs. What options do we have? So we have basically two options. There are industry byproducts or natural products we can use. Industry byproducts are, for example, fly ash, which is a remainder from burning coal sitting at the top of the chimney at power plants. And here we have a replacement of about 30-35% of cement. Our 3101 at the moment allows for 30% replacement. Slag from steel production is much more potent. Slag can easily replace cement up to 90%. However, our standard at the moment says 65% would be the maximum. So everything else would be then an engineered mix, a kind of alternative solution. However, it has been done in New Zealand. I'll talk about that in a minute. And then there's also silica fume, also an industry byproduct from aluminium production and silicon alloy production. The silica fume, the replacement value is about 10%, not really much more, but silica fume is more used to enhance the strength of the concrete. I think you're familiar with our concretes. Our concrete standard 3104 allows for 3 types of concrete: the ordinary concrete, the special concrete, and the prescribed concrete. Ordinary concrete is all concrete between 17.5 and 50 MPa, which comes from a batch with a liability or the testing regime done by the liability by the batch. Concrete above 50 MPa or having more than, let's say, 65% slag replacement, that's special concrete and subject to a concrete materials engineer, and the liability is with the engineer. And then we have the prescribed concrete, which is concrete, self-made concrete in mind. We have the farmer who can't, the concrete truck cannot get there in time, after 90 minutes it goes off. So there's also a prescription of concrete. And so 50% 50 MPa is often used for engineering, infrastructure projects, bridges, or even higher. But silica fume, with silica fume, we get our concrete to, let's say, 250 MPa, which also creates nice and slender elements, or can create nice slender elements. And then the other option is natural pozzolan, something what the Romans used. Volcanic ash, for example, there's an occurrence in the Taupo Central Plateau region near Auckland, but also diatomites, which is in principle compressed algae, an occurrence around the Dunedin area, and silica naturally occurrence we have also in the region of Taupo Rotorua, or more Rotorua, and this is we have undertaken a study with Canterbury University to see replacement levels. At the moment, we talk about 30% replacement levels, and then we still have to ensure access to these natural pozzolans. Obviously, we can't just take away the whole mountain there; it's all mine, no, because we have to consider the environment and cultural heritage and all the things, and have to come to sensible, meaningful decisions. Our standards need a bit of review to allow for higher natural pozzolan replacements. And for you, obviously, you want to know that these new concretes with the cement supplements perform, that they give you the target strength at a certain time. Obviously, they cure a bit slower, so maybe 56 or 90 days is the time to achieve target strength, and not 28 days. We need to educate our technicians and placers as well to deal with the new, to explain them how to best place and work with these concretes. And it must economically make sense, but this is already proven that it would. So the couple of things to consider still. But what else are we doing? What else have we done already within this decisive decade of change? So since August of last year, Holcim have begun operating a large cement blending mill in Auckland Harbour. And here we blend the cement with SEMs to a low carbon concrete, mix glue or cement, low carbon concrete, let's call it cement. and Holcim also imports slag, which has huge potentials regarding cement replacement and thus carbon reductions. So a couple of projects which have been done with low carbon concrete. At the Hunua 4 tunnel, we have used fly ash. We actually achieved a 60% replacement. City railing, one of the very prominent projects, 30 and 40% fly ash mixes have been used. The best, I'm not sure if I say the best, but the highest cement replacement so far was achieved by lease contractors, by a project built by lease contractors still under construction in Christchurch and High Street. It's an office building where they have replaced 70% of the cement. It's a huge benefit. And that would translate to, let's say, roughly 55% of carbon emissions reduction from the concrete per se, just by the cement replacement of 70%. So this is happening at the moment and ongoing with cement replacements ever increasing. And the next stage would be getting our natural supplements more used and market ready. Then as well, on our pathway towards carbon zero, there is a bit of help from the concrete itself. So concrete absorbs carbon dioxide when exposed to the atmosphere, and the exact quantities are described with these collection of formulas from the British Research Establishment, which is an annex to the EPD standard EN 15804. Has been to 2012, but is still an annex to the new version. Not sure if you're aware there's a newer version of EN 15804 2019. There's also a little bit of difference in regards to how biogenic carbon is treated. In the past, in 2012, it could just be deducted, but the new standard says because of the uncertainty at end of life of building materials, in a whole of life scenario, biogenic carbon must come back, must be shown seen as a positive. So a couple of changes in the 2019 version. But however, the formula for the engineers to determine what exactly the quantity of carbon is saved per square meter is described in this Annex C, carbonation of products containing calcium oxide and calcium hydroxide materials such as cement. Carbon capture, utilization and storage is already happening more overseas than in New Zealand. We had it for a short time here, but I'll talk about that in a minute. So this is an example from Heidelberg Cement in Norway. Heidelberg Cement is the largest German cement producer and also one of the largest in the world. And they have a plant in Norway, in Brevik, where they have put this in place already. So the carbon is absorbed by a device, and that's normally manufactured by Linde, one of the largest manufacturer of these devices. They are in the gas business since, I don't know, maybe 150 years. This is transported to the sea, and then the carbon is injected into the ground under a seabed here, 1 to 2 kilometers, into areas where the carbon dioxide finds calcium and oxygen, because it creates a bond with the other elements. So calcium plus oxygen plus carbon dioxide, so Ca plus O plus Ca2 makes CaCO3, which is limestone. So it basically comes back to be stone, to be natural stone. It's kind of like the reverse, what we do in the kilns when we want to separate the lime, so the CaO from the limestone, from the CaCO3, because then if we separate CaO from CaCO3, what remains is CO2. But also Heidelberg Cement have developed a kiln where they separate and collect immediately directly the CO2 without releasing it into the atmosphere. So that's always the case, that other countries have just better options, many more people, more expertise, and also more money to do these things. But it will come to New Zealand sooner or later as well. This is one of the devices, a carbon capture plant from Linde. They do lots of business, and it's quite serious stuff. It's very, very good. Talking about our stakeholders here, Holcim. So we have here an overview of the carbon capture and storage plants and some utilization plants as well by Holcim, but none of these are in operation yet. The first one will start in 2 or 3 years in Greece, which will capture 1 million ton of carbon dioxide. But globally, there are already about 25 carbon capture plants operating, and with many additional ones under development. And this one here, you can see this one is Marston Point. Oil refinery. Their carbon capture plant opened in 2016, but since the previous government supported the closure of the oil refinery, the carbon capture plant has also been shut down. So we need to find new ways to capture our carbon. And as technology becomes more available and affordable, its adoption in New Zealand is really just a question of time. Also, just for your information, you may be interested in this one. I think most of you are familiar with the IStructE, the structural engineers in the UK. And they have online already a collection of initiatives, and there it is documented how it progresses and which stage that is at the moment. And I would just simply recommend to you to check them out if you haven't already. So they're called IStructE, structural engineers in the UK. But just coming back and also more or less concluding with the slide. So this is our concrete road. So before, I had the pleasure to show you what we have already done, replacing coal with waste timber, doing our EPDs, using more and more SEMs, mixing, blending cement with SEMs. But in the essence, our roadmap stands on these 7 columns. The first one is the clinker. So this is still cement production, but as I mentioned, we use biomass waste to fuel the kiln rather than coal. And also aim to get a CO2 capture, direct capture kilns. The next column will be cement and binders, which basically talks about the SEMs, the fly ashes, the slags, the silica fume, and the natural pozzolans. Concrete production at the batch. Also here we try to reduce the cement per cubic meter, really optimizing the mix to get to our, say, target strength, 30 MPa target strength, whatever that is. And then electricity, using more and more electricity, solar energy, also for standby generators, right? Replacing the diesel. That's happening at the plant stage, and also happening at the transport stage, where we replace our trucks with electrical run engines. And Golden Bay have actually commissioned, or actually they have already the first 2 hydrogen trucks, which is quite an achievement. But also it's important that we collaborate together with you guys, with the engineers up front, because only together we can make the difference. So optimizing design, maybe reducing materials, reducing concrete, steel, all the materials as far as we can. And I think this is something you can definitely help us with. And the 6th column would be carbon uptake, which I talked about. The quantities are determined by these formulas with the appendix to EN 15804. And then carbon capture and utilization, which is still still a little bit away in New Zealand, but we will definitely be getting there. So all those 7 columns in combination will get us to carbon zero by 2050. We are very confident we will achieve that. We have this confidence because of our previous success, reducing already 11% of our emissions despite an increase in concrete production. And we now make further progress because we have now availability of cement supplements such as slag here. So Holcim, maybe, I'm not sure if I mentioned that, but Holcim just in August not just opened their mill, they also brought in huge amounts of slag for our concretes. And then we think that 2050 net zero carbon concrete is absolutely realistic for New Zealand conditions. And yeah, with all our efforts, it's important that we work together on this with the government, with the engineers and customers and developers, because it will take all of us in the industry to reach our net zero carbon goal. If we take on our social responsibility, I'm sure we will get to that far more quickly than we thought. And with this last slide here, I would like to say thanks for your attention, but I'm sure you may have questions, even though I'm only here in place of Gamester, our CEO, who was supposed to be here, who is an engineer. So I'm just an architect, but no concrete engineer, but I'll try my best to answer your queries and otherwise forward those questions into the right direction. So thanks for your attention so far, and maybe I stop sharing my screen. Cool. Right. Good, Brendan.
Thank you, Ralf. Yeah, brilliant. Let's open the floor for a couple of questions. Do you want to jump in?
Yeah, Brendan, Neil.
Neil, go for it. Neil, sorry, you're muted.
You're muted, Neil.
Right, there we go. Right, try now. Okay. In recent news broadcasts over the last 6 months, we've seen many photographs of what are purported to be reinforced concrete buildings in the Gaza Strip, which have been totally demolished by high explosives. Now, I appreciate that high explosives, if you hit anything with it, it's going to fall to bits. But is the amount of destruction that we're seeing in Gaza, is that proportionate, or are there other causes? Are the buildings not up to what we would expect from a good standard of construction? Thanks.
Yeah, there are definitely several things to that. First one, you're absolutely right with your assumption that the standards are not as good as here in New Zealand, because as you may well know, New Zealand engineers are definitely maybe if even the best in the world. I mean, we have so many experts here, and they work in all over the world. Look at Nigel Priestley, or look at Rob Jury, look at all these great experts, and yourselves as well, obviously. So our buildings are built to a much higher standard than those in the Middle East. That's one thing, but of course, the first thing is the forces are extreme. And I'd say if we get to that, what the Gaza Strip is experiencing right now, we possibly have other problems than just the structure. So obviously there's something seriously wrong with the societies, or actually with the political landscape there, to allow these terrible things to happen. So the forces are just really extreme, and there's a direct impact and direct explosive aimed at a particular point at the building. So the consequences are definitely different than from our, let's say, standard earthquakes. I'm not too sure what exactly happens. You may be the better experts, and you are the better experts, what would happen in a 500-year event, earthquake event. But generally, the buildings, all the concrete buildings which have been designed properly, they also have performed. I mean, I showed you the examples, or the example of the Women's Hospital, which performed really well, but also other buildings which use a press system, like the L. McDermott building, Dunning Thornton, Alistair at the Kilburn University. So they viscosity modified dampers and all these things. So that's definitely performing. And unfortunately, other countries don't have so great designs. Also, I remember that in Turkey has been an earthquake recently, and it was found that the the buildings were actually not designed as the Turkish standard said they should be because of bribery. The developers, they knew somebody in the council area and said, come on, it's too expensive, can we do something? Yes, we can do something, and now we have the result. So we are again very lucky that we live in a country with definitely one of the least corrupt countries here, and that we can be sure that the buildings in 99% of the cases can be built as the engineers and the reviewers specify. Of course, there are always errors, mistakes, something can happen, but in generally, I'd say we're well better off here. And also luckily we don't have these geopolitical tensions as in other areas of the world. So a bit longer of an answer, but hopefully there's something in it for you.
Thank you. Thank you.
I've got a question, Ralf. Looking at your map, we've only got 25 years to 2050. 34% is going to be is needed for carbon capture. Is the industry doing anything about researching and developing carbon capture on a smaller scale so that we can get that rolled out in our coastal towns and so on, at least to capture it and to liquefy it? I'm sure that New Zealand has got great limestone deposits offshore, which would seem to be calcium, the calcium and the oxygen, you know, and is there any research happening around New Zealand to find places where we can put liquid carbon dioxide?
So firstly, yes, and there are several ways. So one way is in place. Not sure if you've heard of the Canadian company Carbon Cure. So Carbon Cure has come to New Zealand as well, and Stevenson's Concrete have used Carbon Cure for the panels of the Beta Ventura Drive, for example, building, for example. So with Carbon Cure, they have used the CO2 from Marsden Point refinery, brought into the liquid aggregate stage, and then set the tank with the liquid CO2 at the concrete plant at Stevenson. And here, the liquid carbon dioxide was injected into the fresh concrete mix, with a result of 7% reduction in cement. So very similar to if we put carbon dioxide in, let's say, depleted oil reservoirs or in the earth somewhere. The same chemical process happens. There's always some air, some oxygen in the concrete. There's lots of calcium in the concrete, and CO2 connects with those other two elements, and as a result, the quantity of cement can be reduced. So that's the one thing. Now, unfortunately, Marsden Point has been closed, and we are looking, or our stakeholders, some of our stakeholders, looking at setting up some of these linear devices to capture carbon. However, in New Zealand, we only produce cement at Golden Bay, the Golden Bay cement up at Marsden Point. So that's the only place where in New Zealand we produce cement. Then we have imported cement by Holcim, and we have a grinding facility from HR Cement in Tauranga. They import the clinker, but they can mill the cement. So for direct absorption of carbon dioxide from our emissions, we would have to go to Marsden Point. So that sits currently with Fletcher's. They look at those options. Other industry like TY Melting Point, they possibly do their own things. I'm not so familiar now with the steel and metal industry, even though we have a good relation with them. But what they do on detail, I'm not so familiar with. But the options exists, and as I mentioned, it has been done already with Carbon Cure here in New Zealand, and that's the beginning. But as well, we have to see that we can lift the capex for these plants and make it happen. So that's
Is-
yeah, Jess.
Has any work gone into actually, I mean, obviously humanity will need a very good, efficient carbon trading scheme forever now, because there are always products that we need that have a carbon footprint. Is anyone doing any effort in the industry itself to work out how much investment the industry should make into carbon capture research and development, and what happens if it fails, if it doesn't invest in that? What happens? How much can it afford? Because the price of concrete will have to go up, but that's just necessary. It's unavoidable. Has anyone done any costing analysis like that?
Well, we know at the moment that with the cement supplements we are using so far, the slag, the fly ash, there is actually not really a cost difference. So that comes with much low carbon, but at the same costs. And in regards to the capex, that's mostly left to our stakeholders themselves. And at the beginning, they rather look at this on their own for competitive reasons. But we are just starting a journey very soon with a highly funded research into these things. Low carbon and decarbonizing concrete. Carbon capture will be part of that. That's a research funded by MBIE and BRANZ. And there's a good sum for us there for a period of 2 years. And that will definitely be addressed. And we have to look overseas first, obviously, what is existing and how can we implement this in New Zealand. And we are potentially looking at a similar example, similar process like the steel industry with their new facilities, where they have granted a good chunk of money to decarbonize steel production. And as I said, we all sit in this boat together. And if somebody can't carry the whole capex, then I think society is stepping in, because it's really so important that we act fast, and this research is definitely coming right on time, and hopefully by the end of the research in about 2 years we have the answers and have a program in place how we install maybe not one but maybe several carbon capture plants. But as I mentioned earlier, the steel industry will do their things and have done their things already, and in a combined effort, I think we will be getting there. So that's all the answer I can give so far on that. So as you see, it's kind of in development.
Ralf, just picking up on that, you mentioned, the government's given grants to the steel industry to help them decarbonise and introduce recycled steel. Apart from the carbon capture and storage, are there any other capital investments that perhaps you'd like to see the concrete industry take advantage of that might need some assistance from society, as you put it?
Well, we definitely need some assistance from society, but also from policymakers in regards to access to natural pozzolans, where we have then really only the emissions from transport and maybe a little bit from the excavation extraction. So it is something where we need help, and also in making sure that all the standards are right. And New Zealand is a very standard-centric country, but all the work is made voluntarily. So that's why there would be always an option to take a bit of that funding for consultants to look at this with a bit of a speeded up process, if you want. So definitely the standards and the area around natural pozzolans, that definitely needs a bit of help from the government side. And also, as I mentioned, one of our columns to decarbonation is optimized designs. So here we need help from the architects and the engineers to make sure that, I think upfront in collaboration, the architect with the engineer, because I'm an architect myself and I always loved working with the structure engineer, because he could tell me upfront, very, very upfront, how my grid could look like, how my structure could look like. So in the same moment, at the very first meeting before the architect even starts really designing, it's important that you look at options. How can we actually save carbon? What materials could we use? How can we use a bit less carbon? How can we reduce the weight of our structures? There it starts. The lower the weight of the structure, the less, the lower the quantity of the concrete for the foundation needed. So that's definitely something where we need you guys as well. And that goes possibly a little bit too far, but I definitely would appreciate if people, maybe more people, use their push bikes or walk rather than or public transport. I think this is something where we all need to work together, that we make use of these facilities as well. Not so much to do with concrete, but in general, that would be one thing I think most would be appreciated. We could see a bit more of, but then again, you know, with transport, it depends on how fit you are and how far away things are. But yeah.
Any other questions from people?
Just coming back to the carbon capture and storage, is it an energy intensive process? What's the energy cost of doing that?
I'm not familiar with the figures, to be honest. I have to see and ask how much they cost. You would definitely ideally use renewable energy for the process. So I assume it's definitely cheaper here in New Zealand than maybe in Germany, where we don't have as much renewable energy. The figure is around maybe 50% only in Germany, so far behind New Zealand. But I'm not familiar with exact figures of the costs. It wouldn't be as energy intensive in regards to, or carbon intensive, as the actual process you capture the carbon from. But obviously it depends a bit on the source of energy which you are using.
Thanks.
Any other questions? Well, you're thinking.
I've got a question, Brendan.
Oh, yeah, go for it, Gary.
Right, thanks. A great presentation, Ralf. Learned a lot from that. I'm not a structural engineer or a civil engineer, but you said we need to do things quicker. So a question I've got, that you emphasise the durability and the strength advantages of concrete. How do you go about convincing engineers to make use of the new lower carbon options when you haven't had 25 years, 40 years to actually demonstrate that it works? What's your tactics there?
Yeah, so firstly, also not straightforward to answer, or maybe several answers to the question. I don't believe I need to convince them anymore, because at least in my fraternity with the architects, we are actually the drivers of this. We want to reduce carbon, and I think the engineers as well. Obviously, all you want this, because otherwise you wouldn't do the ESR. So I don't think I need to convince them. In regards to performance, well, the example of the Pantheon is a good example. They used other materials. They used volcanic ashes, and it's still standing. We have already smaller projects. I think in Lake Aotearoa in the area. There is also a power station which have used natural pozzolans already. So that was built in the 1950s. So there are even some examples here in New Zealand where we have used the various materials. Fly ash and slag is not new to us. The Meridian building, for example, in Wellington, which is now as well 15 years old, they have used fly ash in their panels and slag in the foundations. So that's not really new to us. It can be done. The problem was always availability. Because we don't have slag readily available, or had, now we have, but because we don't have a steel industry, definitely not a large enough steel industry to provide, to satisfy the demands. But we have now Holcim here, who has brought 100,000 tons of slag, and they can get more because Holcim is, I think it's globally the biggest cement player. They have access to all these cementitious, supplementary, cementitious materials. Fly ash would have to be imported sometimes as well, because normally we get it from Huntley. As you know, that's not always running. So the experience is there. So I wouldn't worry about that. It's more really about security and availability of the materials.
Thanks, Ralf. There's nothing better than learning from history. I don't think we necessarily want to be banking on fly ash from coal because we want to stop burning the coal. But
Of course. I know we
look
definitely
at
define there
yeah.
are. No, absolutely
Ralf.
right. You're absolutely right. Spot on, Gary. Because we definitely don't want to rely on long term on, let's call it, potentially sunset industries. But for now, this material would otherwise just go to landfill and do nothing there. And so now we can just simply replace, so we don't have to produce the cement, which we heard is a bit the culprit of the emissions with concrete. So we just can use that stuff instead. But on long term, yeah, we have to get more to natural pozzolans and focus on that more. Absolutely.
Thanks, Ralf.
Any other questions? Well, I think everyone's sort of had a good run this evening, and we've had a good long session with the talk and the questions. I would like to continue with a few discussion points, but just for the purposes of our video recording, I'd like to wrap things up. And thank you very much, Ralf, for giving us that overview of the developments and in the concrete industry and what's in the plan for meeting the targets you've set, and for answering our questions. We really appreciate it.
Yeah, thanks very much. Thanks again for having me. It was my pleasure. And if there are any questions, please contact us. I think, Brendan, you have all my contact details and maybe Rob's details as well. Just, call us, flick us an email, and we're definitely happy there to help. In particular with the mixes, I think you need to connect to our concrete manufacturers who can deliver low carbon concretes. Okay.